Welcome! Today, we'll be tackling the problem Distribute Candies, an interesting challenge that combines counting, fairness, and optimization. We'll explore how to determine the maximum number of unique candy types Alice can consume if she is allowed to eat only half of the candies. Let's dive in and break this problem down step by step. In this problem, we are tasked with helping Alice distribute her candies. Alice has a total of n candies, and the types of candies are represented by an integer array called candy type. Each unique integer in the array corresponds to a specific type of candy. Now, Alice wants to share her candies equally with her brother, which means she will give exactly half of the candies to him. However, Alice also wants to keep as many different types of candies as she can for herself. The goal is to determine the maximum number of different candy types Alice can eat, given that she can only eat n divided by 2 candies. The input to the problem is the array candy type, and the output is an integer that represents the maximum number of unique candy types Alice can eat. Let's look at the first example to understand this better. Suppose the input array is 1, 1, 2, 2, 3, 3. Here, Alice has 6 candies in total, which means she needs to give half of them, or 3 candies, to her brother. To maximize the number of unique candy types she eats, Alice can choose 1 candy of each type, namely, type 1, type 2, and type 3. This way, she eats 3 candies in total, and all of them are unique. Thus, the output for this example is 3. In the second example, the input array is 1, 1, 2, 3. Alice has 4 candies in total, so she needs to give 2 candies to her brother. To maximize the variety of candy she eats, she can choose 1 candy of type 1 and 1 candy of type 2, or any other valid combination with 2 different types. The maximum number of different candy types Alice can eat here is 2. Now, consider the third example, where the input array is 6, 6, 6, 6. Here, Alice has 4 candies in total and must give 2 candies to her brother. However, since all the candies are of the same type, Alice cannot achieve any variety in her selection. She can only eat candies of type 6, which means the maximum number of different candy types she can eat is just 1. These examples demonstrate how the input array and the distribution constraints determine the variety of candies Alice can keep for herself. Finally, let's discuss the problem's constraints and some key edge cases. The length of the candy type array, n, ranges from 2 to 10,000 and is always an even number. The values in the array, which represent the candy types, can range from -100,000 to 100,000. One important edge case is when all the candies are of the same type, as in the third example here, Alice can only eat 1 unique type of candy. Another scenario is when the number of unique candy types exceeds n divided by 2. In such cases, Alice can only eat up to n divided by 2 types, since that is the maximum number of candies she can keep. Lastly, when n equals 2, Alice will have exactly 1 candy to eat, and the output depends on whether the 2 candies are of the same type or different types. These constraints and edge cases help us understand the problem's boundaries and guide us toward crafting a solution. To solve this problem, we need to maximize the variety of candy types Alice can consume while adhering to the constraint that she can only eat half of the total candies. The array candy type represents the candy types available. First, we observe that the maximum number of candies Alice can eat is n/2, where n is the total number of candies. Second, the number of unique candy types is determined by the size of the set of candy type. From these insights, we can conclude that if the number of unique candy types exceeds n/2, Alice will only be able to consume n/2 unique types. Otherwise, if the unique candy types are fewer than n/2, Alice can eat all of them. This leads us to a simple solution: compute the minimum between the number of unique candy types and n/2. With this understanding, let's explore different approaches to implementing the solution. The first approach is a brute force method, which is simple but inefficient. Here's the intuition: we iterate through the array and manually check each candy type to see if it's unique. To do this, we compare each candy type against all previously counted types. By maintaining a count of unique types, we can then compare this count with n/2 to decide the result. However, this approach has significant drawbacks. The time complexity is n squared, because we repeatedly check for duplicates as we traverse the array. On the other hand, the space complexity is 1, since we don't use any additional data structures. Despite its simplicity, this approach is not practical for large datasets due to its inefficiency. To address this, we can adopt a more optimized strategy using a hash set. A better approach involves leveraging a hash set to track unique candy types efficiently. The key idea here is that a hash set allows us to store unique elements and perform insertions and lookups in O(1) average time. To implement this, we create a hash set and traverse the candy type array, adding each type to the hash set. This ensures that duplicates are automatically handled for us. After processing the array, the size of the hash set gives us the number of unique candy types. Finally, we return the smaller value between len, candy type, /2 and the size of the hash set. The time complexity of this approach is O(n), where n is the length of the array, and the space complexity is O(k), where k is the number of unique candy types. This approach is not only faster but also more elegant compared to brute force. Another alternative is to use sorting to identify unique candy types. By sorting the array, we can count unique types by simply comparing consecutive elements. After counting the unique types, we apply the same logic as before, return the smaller value between n/2 and the unique count. The time complexity here is O(n) log n, due to the sorting step, and the space complexity is O(1) if the sorting is done in place. However, this method has its drawbacks. Sorting introduces additional overhead, making it less efficient for large inputs compared to the hash set approach. While it provides a valid solution, it is not the most optimal choice for this problem. Given the trade-offs, the hash set-based approach remains the most efficient and scalable solution. Here's the Python implementation of the chosen approach using a hash set. We first compute the number of unique candy types by converting the array into a set, which automatically removes duplicates. The size of this set gives us the count of unique types. Next, we calculate the maximum number of candies Alice is allowed to eat, which is len, candy type, /2. Finally, we return the smaller value between these two numbers. This implementation is concise, efficient, and leverages the properties of the hash set to handle duplicates seamlessly. It achieves O(n) time complexity and is well suited for handling large inputs, making it the optimal solution for this problem. In this problem, Alice has a collection of candies represented as an array called candy type, where each element corresponds to a specific type of candy. The challenge is that she can only eat half of the total candies, determined as n/2, where n is the length of the array. Our goal is to figure out the maximum number of unique candy types she can consume given this restriction. To solve this, there are two key constraints to consider. First, the maximum number of unique candy types Alice can eat is limited either by the total number of unique candy types in the array or by n/2, whichever is smaller. Second, we can achieve this efficiently by counting the unique candy types in the input and comparing this count with n/2. By using a hash set to track unique types, we can determine this in O(n) time, which is optimal compared to other approaches like sorting. The high-level algorithm involves counting the unique candy types, comparing the count with n/2, and returning the smaller of the two values. To break down the solution step by step, we start by reading the input array candy type. From this, we calculate n, the total number of candies, and determine max allowed, which is n/2, the maximum number of candies Alice can consume. Next, we count the unique candy types using a hash set. By iterating through each candy in the array, we add it to the set if it's not already present. The size of the set at the end of this process gives us the total number of unique candy types. Finally, we compare the total number of unique types with max allowed. If the number of unique types is less than or equal to max allowed, Alice can eat all the unique types. Otherwise, she can only eat up to max allowed types. There are also some edge cases to keep in mind. If the array is empty, the result is 0 since there are no candies. If all candies are of the same type, the result is 1 because there's only one unique type. And if there are more unique types than n/2, the result is capped at n/2 since that's the maximum she can consume. The hash set is the key data structure we use in this solution. It allows us to store unique candy types efficiently, with average time complexity of O(1), for insertions and lookups. This makes it more suitable than a list, where checking for uniqueness would take O(n) for each element. In terms of time complexity, iterating through the candy type array takes O(n), and with hash set operations being O(1) on average, the overall time complexity remains O(n). For space complexity, the hash set requires additional space proportional to the number of unique candy types, denoted as k. In the worst case, where all candies are unique, this means OK equals O(n). To implement the solution, we define a function maxCandies that calculates the total number of candies, determines max allowed, and counts the unique candy types using a set. Finally, we return the smaller number between the unique count and max allowed using Python's min function. Let's walk through an example to solidify our understanding. Suppose the input is candy type equals 1, 1, 2, 2, 3, 3. Here, the total number of candies n is 6, which means max allowed equals 6/2 equals 3. We initialize an empty hash set and begin counting unique candy types by iterating through the array. Adding the candies to the set results in the unique types 1, 2, 3. The size of the set is 3, so unique types equals 3. Comparing this with max allowed, we take the smaller of the two values. Since unique types equals max allowed, the result is 3. This means Alice can consume 3 unique candy types. Now consider an edge case. If the input is candy type equals 1, 1, 1, 1, we again calculate n equals 4, so max allowed equals 4/2 equals 2. As we add candies to the hash set, we end up with only one unique type, 1. In the edge case where all candies are of the same type, the total number of unique types is 1. Here, unique types equals 1, and max allowed equals 2. Since we return the smaller value between these two, the result is min, 1, 2, equals 1. This makes sense because even though Alice is allowed to eat up to 2 candies, she only has one unique type available. By following this approach, we handle both typical inputs and edge cases efficiently, ensuring that we always return the correct maximum number of unique candy types Alice can consume. The solution begins by defining a function distribute candies inside the solution class, which takes candy type as input. This input represents an array of integers where each integer corresponds to a type of candy. The first step is to determine the maximum number of candies Alice can consume. Since she is allowed to eat only half the candies, we calculate this as max_to_eat equals len, candy type, //2. Next, we calculate the number of unique candy types using the set data structure. By converting the candy type list into a set, duplicate values are removed, and the length of the set gives the count of unique candy types, unique_candies equals len, set, candy type. Finally, the problem requires us to return the maximum number of unique candy types Alice can eat. This is constrained by either the number of unique candy types, unique_candies, or the total candies she is allowed to consume, max_to_eat. Therefore, we take the minimum of these two values, return min, max_to_eat, unique_candies. This approach effectively balances between the constraints of how many candies Alice can eat and how many unique types are available. The solution is efficient with a time complexity of O(n), where n is the length of candy type, due to the conversion of the list to a set, and a space complexity of O(k), where k is the number of unique candy types in the input array. This is the Java implementation of the LeetCode problem number 575, distribute candies. The solution mirrors the logic of the Python implementation, calculating the maximum number of unique candy types Alice can eat. Key differences in the Java version include the use of a hash set to count unique candy types and explicit type declarations for variables. The method distribute candies accepts an array of integers representing candy types and returns the result based on the minimum of the maximum candies Alice can eat and the unique candy types available. In this problem, we are tasked with helping Alice maximize the number of unique candy types she can eat, given that she is only allowed to eat half of the total candies. The input is an array called candy type, where each element represents a specific type of candy. Let's start with a basic example where all the candy types are unique. The input array is 1, 2, 3, 4. First, we calculate the maximum number of candies Alice can eat, which is half the total number of candies. Since there are 4 candies in total, max_to_eat is 4/2 equals 2. Next, we count the unique candy types using a set. The unique types in this array are 1, 2, 3, 4, so the total number of unique types, unique_candies, is 4. Now that we know Alice can eat at most 2 candies and there are 4 unique types available, we need to determine how many unique candy types she can eat. To do this, we take the minimum of max_to_eat and unique_candies. In this case, the minimum of 2 and 4 is 2. Therefore, Alice can eat 2 unique candy types in this scenario. Let's consider another example where the input array is 1, 1, 2, 2. First, we calculate max_to_eat as before. The total number of candies is 4, so max_to_eat equals 4 //2 equals 2. Then, we count the unique candy types using a set. In this case, the unique types are 1, 2, so unique_candies is 2. With this new input, Alice can still eat at most 2 candies, but this time there are only 2 unique types available. To determine the result, we again take the minimum of max_to_eat and unique_candies. The minimum of 2 and 2 is 2, so Alice can eat 2 unique candy types. Let's extend this idea further with an example where there are many duplicates. The input array is 1, 1, 1, 1, 2, 2. Here, the total number of candies is 6, so max_to_eat equals 6 //2 equals 3. Next, we count the unique candy types. The unique types in the array are 1, 2, and unique_candies is 2. In this third example, Alice is allowed to eat up to 3 candies, but there are only 2 unique candy types available. Again, we take the minimum of max_to_eat and unique_candies to determine the result. The minimum of 3 and 2 is 2, meaning Alice can eat 2 unique candy types. To summarize, the algorithm involves 3 main steps. First, calculate max_to_eat as half the total number of candies. Second, find the count of unique candy types using a set. Finally, return the minimum of max_to_eat and unique_candies. This ensures that Alice eats the maximum number of unique candy types while adhering to the constraint of eating no more than half the candies. To analyze the time complexity of our solution, let's break it into its key steps. First, determining the length of the candy type list is a straightforward operation that takes constant time, or O(1), since Python has a built-in mechanism to retrieve the length of a list. The most computationally expensive part comes next, constructing the set from the candy type list. This involves iterating through each of the n elements in the list and inserting them into the set. Since the average time complexity for inserting into a set is O(1), iterating over all n elements results in an O(n) operation for this step. After the set is constructed, calculating its length is another constant time operation, O(1), as Python sets store their size as metadata. Finally, the division operation to calculate half the list length and the comparison using the min function are both O(1) operations as well. Putting this all together, the dominant operation is constructing the set, which takes O(n). All other steps are constant time, so the overall time complexity of the solution is O(n). Now, let's look at the space complexity of the solution. First, we have the input storage. The candy type list itself takes O(n) space to store its n elements. Next, we consider the space required for the set that is created from the candy type list. The set will store only the unique elements, so if we denote the number of unique elements as k, the space required by the set is proportional to k. In the worst-case scenario, where all n elements are unique, k equals n, and the space required by the set is O(n). Finally, the solution uses a small number of auxiliary variables, such as max_to_eat and unique_candies, which require constant space, or O(1). Therefore, the space complexity of the solution is dominated by the set, making it OK. In the worst case, where k equals n, the space complexity simplifies to O(n). Let's compare this solution to a naive approach. A naive implementation might involve manually counting the occurrences of each candy type using nested loops. This would result in a time complexity of O(n², which becomes impractical for large inputs, though the space complexity would remain O(1), since no additional data structures are used. The current solution, by contrast, is much more efficient. Using a set allows us to count unique candy types in O(n) time, avoiding redundant computations and leveraging the efficiency of set operations. The space complexity of O(n) is also reasonable, as it scales linearly with the input size. For best-case scenarios where the number of unique candies is significantly smaller than the total number of elements, the space used by the set is reduced, although the time complexity remains O(n). On average, with random inputs, the time complexity is O(n) and space complexity is O(k). In the worst case, where all candies are unique, both time and space complexity are O(n). The mathematical justification for the big O here is straightforward. Since constructing the set is the dominant operation and scales linearly with the input size, the overall complexity for both time and space is O(n). Here, we'll look at some common mistakes to avoid when solving the distribute candies problem. First, not accounting for uniqueness properly is a frequent issue. Some mistakenly count the total number of candies instead of focusing on the unique types. This is incorrect because the goal is to maximize the number of unique candy types Alice can consume, not the total count. Another common mistake is failing to respect the maximum limit of candies Alice can eat, which is half of the total candies. If the number of unique types exceeds n divided by 2, the result must still be capped at that limit. Finally, inefficient implementations can also lead to problems. For instance, using nested loops to count unique candy types results in an O(n) squared time complexity, which is unnecessary. A hash set is a much more efficient way to determine uniqueness in O(n) time. In addition to those, there are other pitfalls to watch out for. Ignoring edge cases is one of them. For example, with small inputs like a single candy or two identical candies, it's important to ensure the solution respects both the uniqueness of candy types and the limit of n divided by 2. Another mistake is misunderstanding the problem constraints. Some might assume that candies are always distinct or that the input size is always large. Overlooking these details could lead to over-engineering the solution or inefficient handling of smaller cases. It's crucial to account for all possible scenarios and constraints when crafting your approach. From an interview perspective, this problem emphasizes the balance between maximizing unique candy types and adhering to the n divided by 2 limit. A hash set or dictionary is an ideal tool for efficiently tracking unique types. To optimize further, you can terminate early once the size of the unique set reaches n divided by 2, saving computation time. This problem also demonstrates a common pattern of balancing constraints, which shows up in other challenges like subsets or distributions. When solving this in an interview, it's important to communicate effectively with your interviewer, clarify edge cases, such as small arrays or identical candies, and confirm you understand the constraints before you start coding. Related problems, such as majority element, contains duplicate, or longest consecutive sequence, can help you recognize similar patterns and refine your approach. Now, let's explore some alternative approaches and their trade-offs. The hash set approach is the most efficient for this problem. By using a hash set to track unique candy types and returning the minimum of the unique candy count or n divided by 2, you achieve O(n) time complexity with O(n) space. This method handles all constraints effectively. Next, there's the sorting and iteration approach. Here, you sort the candies first and then count unique types in a single pass. While this reduces space usage to O(1), it increases time complexity to O(n) log n due to the sorting step, making it slower for large inputs. Finally, there's the brute force method, which uses nested loops to count unique types. Although it's the simplest to implement, it's highly inefficient with O(n) squared time complexity and is not suitable for larger inputs. Each approach has its merits, but the hash set method is generally the best choice for this problem. Great job! To recap, we explored the distribute candies problem and saw how set-based approaches can simplify counting unique elements under constraints. Remember, problems like this help sharpen your skills with hash-based data structures and optimization. Thanks for watching, and don't forget to like, share, and subscribe for more coding insights. Keep practicing, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!